On a calm, ordinary morning along Japan's northeastern coast,
Tectonic plates deep beneath the Pacific Ocean suddenly shifted by 50 meters in less than 3 minutes.
a fault line tore open, displacing billions of tons of seawater and sending a tsunami racing toward the shoreline at the speed of a jet airliner. Within an hour, coastal defense walls across the region collapsed. More than 120,000 buildings were reduced to debris, nearly 20,000 lives were lost, and the Fukushima Daiichi nuclear disaster triggered cascading technological failures across an entire nation. On March 11, 2011, humanity's greatest coastal defenses had utterly failed. In the painful aftermath of this tragedy, Japan refused to surrender its coastline. Instead, the nation embarked on one of the most audacious, expensive, and controversial engineering efforts in human history, a $12 to $17 billion megastructure stretching 400 kilometers along the edge of the Pacific Ocean. This is the story of how structural engineers abandoned centuries of traditional defense to design a revolutionary system capable of absorbing nature's absolute fury, and how this colossal monument to human ingenuity accidentally created a dangerous human flaw that no amount of concrete could fix.
To understand why a 400-kilometer wall was built, engineers first had to understand why the original structures disintegrated so fast.
What researchers discovered when analyzing the wreckage was completely unexpected. The walls didn't primarily fail because waves struck them head-on. They failed because the ocean found a far more insidious path. As gigantic waves poured over the barriers, the returning water became just as dangerous as the incoming flood. It ripped away the soil supporting the foundations from behind, a destructive process known as backwash scour. The concrete blocks often remained intact until the ground beneath them disappeared. The walls collapsed because their foundations had been quietly washed away from behind. Confronted with a force capable of crushing reinforced concrete like dry glass, Japanese engineers faced a fundamental dilemma. Building taller walls was simply not the answer. Inspiration for a completely new strategy came from a surprising historical precedent. Decades earlier, the fishing village of Taro had constructed an unusual X-shaped seawall after devastating tsunamis in 1896 and 1933. In 2011, even those barriers were overtopped. Yet, something remarkable happened. Their intersecting geometry absorbed kinetic energy, redirected water, and delayed destruction just long enough to save countless lives. Engineers realized the lesson was not that the walls had failed, but that redundancy had succeeded. A structure could still fulfill its ultimate purpose even when the ocean climbed over it. That realization triggered a fundamental paradigm shift. Engineers stopped treating seawalls as indestructible shields meant to block nature. Instead, they designed a multi-layered defense system built around one core philosophy: resilient delay. To handle two completely different scales of disaster, the new 400-kilometer wall was engineered with a dual mechanism. It completely blocks level 1 waves, which occur every 50 to 160 years, protecting homes, roads, and critical infrastructure. But for rare level 2 events, the design philosophy changed dramatically. The barrier features a unique outer concrete crown angled at 10 degrees to reflect incoming wave energy back into the ocean. Even if a wave overtops the structure, deep 25-meter foundations and reinforced drainage systems keep the wall standing, absorbing the impact and buying precious minutes for residents to reach higher ground. Yet, turning this theoretical blueprint into reality forced engineers to contend with terrain that money alone could not solve. Japan's coastline is anything but uniform. On soft clay, 40-ton excavators would sink without specialized support. Engineers solved this by laying vast networks of steel plates, distributing the machinery's weight so effectively that the excavators almost floated across the mud. In sandy areas, deep sheet piles stabilized the foundations, while along rocky coastlines, workers drilled directly into bedrock, fastening the wall to the mountains. The challenge intensified as construction pushed directly into the turbulent surf zone, where underwater currents created zero visibility conditions that made human diving impossible. Construction teams were forced to place 5-ton foundation rocks with pinpoint accuracy, relying entirely on real-time sonar systems. Before a single section of concrete was poured, researchers conducted more than 200 numerical simulations and wave tank experiments. Ground preparation demanded an extraordinary standard known as 98% Proctor density. A poorly compacted foundation could settle by hundreds of millimeters in a single day, creating weaknesses capable of destroying an entire wall. Every layer was measured, tested, and compacted until virtually no movement remained. Every single section required absolute precision. To prevent internal erosion, engineers integrated geotextile membranes and used self-compacting concrete to eliminate hidden air pockets around reinforcing steel.
Inspectors tested the concrete using acoustic hammer clang tests, immediately discarding any panel that produced a hollow sound.
To absorb the ocean's violent energy long before it reaches the main wall, engineers deployed thousands of 32-ton concrete blocks called tetrapods directly into the surf zone. Arranged in an interlocking pattern, these four-legged structures create a porous matrix that dissipates wave energy through turbulent friction. Instead of slamming into a smooth barrier, the ocean wastes part of its energy fighting its own chaotic currents. However, hundreds of rivers and active commercial harbors required open pathways to the sea, creating dangerous gaps in the primary barrier. To protect these vulnerable openings during emergencies, engineers installed 443 automated floodgates. Equipped with seismic sensors, the gates automatically slide shut within 70 seconds after an earthquake. Many also rely on fail-safe gravity drop mechanisms that operate even if the regional electrical grid collapses. Even with construction complete, the engineering system never truly shuts down. Embedded sensors continuously monitor settlement, pressure, vibration, and structural strain in real time, while annual emergency exercises verify that the entire network remains fully operational. On paper, this 400-kilometer megastructure stands as a monument to human engineering brilliance. But behind the concrete lies a deeply unsettling human truth. Along the coast, 15-meter walls now block the horizon, severing communities from the ocean that shaped their culture and sustained their fishing economy for generations. Residents describe a claustrophobic sense of isolation, feeling trapped behind a concrete prison. Marine scientists also warn that altering the natural exchange between land and ocean disrupts nutrient cycles and fragile coastal habitats. Even more dangerous is a subtle psychological trap uncovered by researchers at the University of Tokyo, the phenomenon of moral hazard. Studies show that the physical presence of high seawalls creates a false sense of absolute security, delaying human evacuation times by up to 30% during a crisis, as residents assume the concrete will protect them instead of immediately fleeing to higher ground. This creates a haunting contradiction at the heart of the project. The very structure built to save lives can unintentionally erode the vigilance needed to survive a tsunami. To address this psychological vulnerability, planners are expanding into hybrid defense models. Programs like the Megaproject are planting coastal forests on artificial earth mounds, where deeply rooted trees help slow floodwaters, while entire communities are systematically being relocated to higher ground. Japan's Great Wall is ultimately a lesson in the limits of human power. This 400-kilometer experiment in risk management proves that no amount of concrete can truly master the ocean. Instead, it serves as an engineering buffer designed to buy precious time, while the real key to survival remains human awareness and rapid evacuation. As sea levels rise and extreme weather events become more frequent, this project stands as a global test case for how far civilization can go to protect its shores.
Let us know in the comments, do you think massive concrete walls are the right long-term strategy for coastal defense? Or should societies retreat inland and adapt to the natural movement of the ocean?